Sauce here. This is a video lesson on integrals, the properties of integrals that involve their bounds. We have an integral. This is an elongated S integral sign. The bounds of integration are from a to b. The integrand is f of x, and the dx is what we call with respects to x. So this represents the area under the f curve from a to b. The bounds of integration are a to b. I'm going to draw an example. If we have a piecewise function that has a linear piece that transitions to what looks to be a quadratic piece, then the bounds of integration we could represent as a lower bound and an upper bound, and that area that comes from the integral is the area between this f function and the x-axis. So this is a single function. It's piecewise, so it'll have at least two expressions for the different pieces that we can see, and there's a transition point from one piece to another. How would we write the area under the curve of this function if in the integral we have one expression for f? This is a piecewise function, so there's more than one expression. We can't put both the expressions into the same integral. We're going to have to separate the integral at the transition. Transitions from a linear piece to a quadratic piece, so I can express the area under this curve as the sum of these two regions. The area from a to c of f would then have only the expression for the linear piece put into this integral if the bounds of integration were from a to c. And then it transitions from c to b to using a different expression, but it's the same function with respect to x. In other words, to find the area under a curve like this required separating the integral into two, which can be done. Each of these expressions or each of these integrals calculates a different region under a different expression, and the sum then is the entire region. As long as the bounds of integration are seamless and don't overlap, we go from a to c and then from c to b. No overlapping bounds and a seamless transition at c. This highlights a property of integration, that we can break up a definite integral into more than one integral and add them together as long as the bounds of integration form an interval that is seamless and does not overlap. This is a general property of integration. It does not require a piecewise function, but it works for this. Here's another property of integration. We could have a function, we'll call it g, and we could integrate. We have bounds from a to b, and we could write the integral from b to a under g with respects to x, which would be represented on the graph by this area. I didn't make a mistake in writing the bounds, but notice that what is in the lower bound position will be the higher value. I'm integrating from b to a. That means that I'm integrating backwards. What's the difference? Well, remember that the definite integral came from the sigma notation that adds up rectangle areas, that the dx represents the change in x or the base of those rectangles. G of x represents the height. It's the base of the rectangles that I'm finding by going backwards, which means that I will produce a base that is negative if I start with a higher value and head towards a lower value. If I'm multiplying by a base that is negative, it'll make the entire area of the rectangle negative, and this region then will be a negative region, or if we produce a value, that value will be negative, and the area will be representing a negative number. That's okay. Area can only be positive, but we can have an area represent a negative quantity. If I took the integrand and I wanted to find the area by going forwards, then I could change the bounds of integration from a to b, low to high, which means that I would change dx to be a positive number because I'm going from low to high, and to represent the negative, I put it out front instead. In other words, I can switch the bounds of integration as long as I then switch the sign of the entire integral. This is a property of integrals that works for every function. One other property, the integral from a to a of f of x with respect to x. Let's think about what it means when the bounds of integration are the same number. Again, it might help to remember that we're calculating areas as base times height, or roughly in concept. So if I start calculating an area under the curve, and I have literally 0 width in my interval, then it's like multiplying by a base of 0, which means it doesn't matter what the function value is, the area is going to be 0. So as a general property of integration, if the integral includes a bounds where the same number is used for both the higher and lower bound, it's going to produce a 0 value, which represents a 0 area.